Hi everyone, I'm Chao Wang from the Chinese University of Hong Kong, and I will introduce our work SEPH, which is a scalable, efficient, and predictable hashing on persistent memory. If we revisit the classical memory hierarchy, there actually exists a huge gap between the memory and storage. Fortunately, the byte-addressable persistent memory can fit in the huge gap with storage-like capacity and memory-like speed. The persistent memory is a collective term which refers to a wide-range memory technology sharing some common properties. The first PM product, Intel Optane, is commercially available in 2019. It provides large capacity per DIMM with persistence and DRAM level latency, bandwidth, and load store support. Even though PM sounds great and promising, there is differences between the DRAM and PM. For example, the read latency of PM is 2 to 3 times compared with DRAM. The bandwidth of PM is 1/6 to 1/3 of that of DRAM. Thus, many recent studies advocate to retailor, index, and algorithm for PM, for example, tree and hashing. Today, we are going to focus on hashing because it provides constant scale query time complexity, which is attractive to the in-memory system, such as in-PM database. Existing PM hashing scheme can be categorized into 2 series. The first one is named level-based PM hashing, including level hashing and C-level hashing. Since resizing a hash table is very time-consuming, the key idea is to bring out an innovative 2-level structure and a cost-efficient resizing algorithm to mitigate the performance degradation during the resizing. As the figure shows, when the hash table is full, they allocate a new, larger space with twice the size of the top-level hashing. And then it only rehash the key item in the bottom level to the new space. After the rehashing, the bottom level can be reclaimed. Only 1/3 key item in the hash table are rehashed because the size of the bottom level is 1/3 of the full table. The second existing PM hashing is named EH-based PM hashing because it inherits the basic structure from the extendable hashing. This series includes CCEH and Dash. And the basic idea is to manage the table in a smaller granularity called the segment. This is to say, when a segment is full, they will allocate a new segment and rehash all the key items in the original segment and move half of them into the new segment. Moreover, they proposed cache line conscious design to achieve a higher throughput, such as aligning the bucket to the cache line size to access the bucket efficiently. However, through our empirical evaluation, we discovered the existing PM hashing face a dilemma between the performance efficiency and predictability. At the right-hand side, EH-based PM hashing has better efficiency with higher average throughput, which is indicated by the red line in the figure. But the real-time throughput fluctuates seriously because of the high overhead segment split, which is indicated by the blue shaded area. At the left-hand side, the level-based PM hashing has better predictability because of the low overhead resizing, but the average throughput is not as high as the EH-based PM hashing. What's more, we find the performance scalability of existing PM hashing is limited due to the excessive right in handling the concurrency control. Thus, we propose SEPH, which is the first PM hashing achieve good scalability, efficiency, and predictability at the same time. SEPH breaks the dilemma between the efficiency and predictability by proposing the level segment structure and low overhead split. SEPH achieves a good scalability by proposing semi-lock-free concurrency control. And next, I will introduce them in details. The level segment structure is a novel structure proposed to combine the respective strengths of the two series of PM hashing. As a figure, SEPH also has many segments like EH-based PM hashing, and we call them physical segment here. The difference is SEPH manages these segments in a level style. This is to say, 1.5 physical segments form a level segment, which is a logical two-level structure. With the physical segment, SEPH inherits the cache line conscious design from EH-based PM hashing to achieve good efficiency. While with the level segment, SEPH is potential to achieve cost-efficient resizing for good predictability. To suppress the performance unpredictability caused by the high overhead of segment split, we propose two low overhead split algorithms. And the first one is named 1/3 split, because it splits a level segment into two, but only rehash 1/3 of the KV items. For example, we are going to split LS0 here. First, we allocate two new physical segments here, and then we only rehash the KV item in the low-level buckets. And then, after the rehashing, two new level segments are formed, and the lower level bucket can be reclaimed. Therefore, one level segment is split into two, but only 1/3 KV item in a level segment is rehashed. We found the overhead of split can be further reduced. A common practice to support the variable length key is to store the KV pointer in the hash table. However, rehashing requires to dereference the pointer to calculate the hash key. These pointer dereferences are usually PM random rate, which is unfriendly to PM. So we propose dereference-free rehashing to eliminate this pointer dereference. In our 1/3 split, only 2 bits of the hash key are needed for rehashing to know where to place the rehashed KV items. So we propose to store these bits in advance as a failure of the KV's future position. In our implementation, we store 16 bits failure with the KV pointer. Considering the failure can be used up with many rounds of rehashing, we update them in the background. As mentioned before, the scalability of existing PM hashing is bad because of the excessive PM writes for the concurrency control. Specifically, in the lock-based design, the excessive PM writes are used to manage locks. In the lock-free design, the excessive PM writes are used to guarantee the correctness. SEPH solves this by only letting the frequent operations such as insertion, search, update, and deletion be lock-free to save the PM writes in the most cases, while let the infrequent but critical operations such as split be lock-based to ease the correctness guarantee. Thus, SEPH achieves nearly minimum PM writes and scale well. We compare SEPH with the state-of-the-art designs, and all the experiment is conducted on the Intel platform with Optane 100 series in APP direct mode. The first result shows SEPH has good efficiency with at least 2 times better average throughput. And at the same time, SEPH has good predictability with the best worst-case throughput, which is even larger than the peak throughput of other designs. Then SEPH has a good scalability in terms of insertion, update, and deletion, and SEPH provides competent search performance under high concurrency, thanks to the semi-lock-free in minimizing the PM writes. To figure out how the proposed technique contributes to the overall performance, we conduct the performance down by equipped SEPH with semi-lock-free 1/3 split and dereference-free rehashing 1 by 1. And by comparing the 2 variants of SEPH, it demonstrates the semi-lock-free lifts the maximum throughput by about 17%. And the reason is it reduces the PM writes by about 60%. Second, 1/3 split lifts the minimum throughput by 70%. And the reason is it reduces the resizing time by half. And lastly, the dereference-free rehashing further lifts the minimum throughput by about 50%. And the reason is it significantly reduces the resizing overhead. As a summary, SEPH breaks the dilemma between the efficiency and predictability by proposing level segment structure and lower head split algorithm to combine the strengths of existing 2-series PM hashing. SEPH achieves good scalability by proposing the semi-lock-free concurrency control to minimize the PM writes for concurrency. SEPH is rigorously validated on the real-world PM hardware and demonstrates its potential value to the time-sensitive application. Thank you.